Hi, this is Dr. Habib Ahmed. On popular demand of a lot of local and international students, I am hereby presenting a video on the Silvaco TCAD simulation of aluminum gallium nitride HEMT. Let me introduce you to a few basics of high electron mobility transistor, and then we will focus on the Silvaco TCAD simulation of aluminum gallium nitride HEMT. HEMT, which stands for High Electron Mobility Transistor, is also known as heterostructure field effect transistor, or we can also call it modulation doped field effect transistor. It is a field effect transistor in which we have a junction between a wide bandgap material and a relatively narrower bandgap material. Like for example, if we are talking about the aluminum gallium nitride HEMT, we have the aluminum gallium nitride layer over here, as you can see from the reference color chart, and aluminum gallium nitride is a wider bandgap material, as you can see from the energy band diagram as well, while gallium nitride is a relatively narrower bandgap material as compared to aluminum gallium nitride. The bandgap of gallium nitride is 3.4 electron volts, and the bandgap of aluminum gallium nitride can be tuned in the range of 3.4 to 6.2 electron volts depending on the aluminum content. Excuse me. Like for example, in this case, I'm using a 30% aluminum content for the aluminum gallium nitride layer. If you use a larger content of aluminum in the ternary alloy, we will see an even higher or even wider energy band gap for the aluminum gallium nitride layer. So, a HEMT actually uses this junction, or the interface, or we can also call it the heterojunction, this junction over here between the aluminum gallium nitride and gallium nitride layer, as a channel instead of a channel between doped regions. For example, we see in metal oxide semiconductor field effect transistors that there is a drain and there is a source, and a channel is formed between the drain and the source. On the other side, in case of high electron mobility transistor, this interface over here actually acts as a channel, as we are going to see slightly later. HEMTs are used in integrated circuits as digital on-off switches. HEMT transistors actually enable us to operate at higher frequencies than ordinary transistors, and they are used in high frequency products such as cell phones, satellite television receivers, voltage converters, and radar equipment. Now, some examples of HEMTs are silicon germanium based HEMT. Another example is aluminum gallium arsenide based HEMT. But aluminum gallium nitride based HEMT has recently attracted a lot of attention due to their high power performance. Gallium nitride based HEMTs have some specific advantages. For example, it can operate at higher operating temperatures. It has higher breakdown strengths. For example, the breakdown field of gallium nitride is we can also call it the critical field, is 3 megavolts per centimeter, as compared to silicon, for which the breakdown field is 0.3 megavolts per centimeter. Also, gallium nitride results in lower specific on resistances, which is another advantage for gallium nitride based HEMTs. In HEMTs, the electric current flows between the drain and the source. Like for example, over here in this structure, if I display the contacts as well, apply. So this is my drain and this is my source. and the current flows between the drain and the source via the interface. So if I zoom in on this structure over here, this is the interface between the aluminum gallium nitride and gallium nitride based layer, and the current flows right across this interface because of the formation of two-dimensional electron gas, which is located at the interface between the two layers, between the wide bandgap material and the narrower bandgap materials. A two-dimensional electron gas occurs when electrons are confined to an interface between two different materials. For example, here we see on the left side we have the band gap for the aluminum gallium nitride layer, and on the right side we have the energy band diagram for the gallium nitride layer. And because of this heterojunction, we see this kink over here, which is a result of the spontaneous polarization and piezoelectric polarization between the gallium nitride and aluminum gallium nitride layer. So electrons are going to be confined to this kink over here, and generally we know that electrons have a tendency to move to the bottom of the conduction band. So electrons are going to move towards this kink from the gallium nitride layer and also from the aluminum gallium nitride layer. By the way, this band diagram is under thermal equilibrium. So HEMTs actually make use of these electrons at the heterojunction. The heterojunction is created by different bandgap materials, as I already discussed, and it forms a quantum well. Now the electrons are actually confined inside this quantum well, and since these electrons are confined, they can actually move quickly without colliding with any other kind of impurities, and these electrons cannot actually escape from this quantum well. Well, these electrons also do not collide with any other impurities, because generally a high electron mobility transistor is based on undoped or extremely low doped materials, like the gallium nitride layer over here is undoped and the aluminum gallium nitride layer over here is undoped. Naturally, or we can say inherently, there is still some sort of electron concentration in gallium nitride, but HEMTs are actually based on undoped or extremely low doped materials, and because of that, these electrons they are confined to the channel, but they also do not collide with any other impurities, resulting in higher mobility for these electrons. So the effect of this is that there is a really thin layer of highly mobile conducting electrons with very high concentration. This also gives the channel extremely low resistivity, or in other words, we can say high electron mobility. Now we know that in gallium nitride, aluminum nitride, indium nitride, and also in the ternary alloys, aluminum gallium nitride is one of the examples of a ternary alloy between gallium nitride and aluminum nitride. There is hexagonal structure asymmetry, which results in spontaneous polarization. And then we know that there is going to be lattice mismatch between the aluminum gallium nitride layer and the gallium nitride layer. And because of this lattice mismatch, we experience piezoelectric polarization between these two layers, forming a heterojunction which looks like this. Now, let me focus. Let me focus on the code now. I'm gonna close this figure as for now. And also just to show you that the current excuse me, so this figure, this structure is actually at a gate voltage of 0 volts and a drain voltage of 30 volts. Here we can see that if I go to contours and then if I look at for example, we can look at polarization charges concentration, hit apply. And if I zoom in on the figure, we see that the polarization charges are actually confined to the channel. Similarly, and then I zoom out once again. Similarly, I go to contours, and if I click on the total current density, and then I hit apply once again. Okay. And when I click on the structure, then we see that the current density is actually confined to the channel between the aluminum gallium nitride and the gallium nitride layer. I click on display, contours, define contours. If I click on this, so now this gives a better idea of the structure. The current density, as you can see, is approximately 0 elsewhere in the structure. However, if we focus on this channel, now we see that we can also check it from the reference color chart that the current density is actually confined to this channel between the aluminum gallium nitride and the gallium nitride layer. And we can also look at the current flow lines. So I go back to contours and I click on current flow lines over here and I hit apply. So, and then I zoom in on this heterojunction. So now you can see that the current flow lines are actually confined to this interface between the aluminum gallium nitride and the gallium nitride layer. You can see them further. You can see like denser current lines over here right at the interface. Excuse me. Okay. Hit display. Okay, so now we will talk about the code from scratch. Hit OK. Here I've already created the code. Here is the deck build interface. But generally, like, the font size is really small in deck build, so I've copied my code into Microsoft Word file, and we are gonna look at the Microsoft Word file where we have the Silvaco TCAD code for aluminum gallium nitride HEMT. We start with Go Atlas, and then we define a meshing where the meshing is running from 0 to 10 micrometers in X direction, and then I've defined different spacings. So if I go to the structure, right click on the structure, hit display, and then I click on meshing, you can see the structure. The structure is running from 0 to 10 micrometers in the X direction, and I've defined denser meshing over here in the X direction because we have the gate electrode over here right at the top. Then let's talk about the Y meshing as well. So in Y direction, I would define a really denser meshing at a location of 0 to 0.03, which stands for 30 nanometers. 0.03 micrometers is actually 30 nanometers. You might already know that the by default units in Silvaco TCAD are micrometers. So from 0 to 30 nanometers, I would define a really dense meshing. As you can see over here, from 0 to 0 to 30 micrometers, I've defined a really dense meshing, because over here we have the thin aluminum gallium nitride layer. So the thickness, I've kept a thickness of 30 nanometers for the aluminum gallium nitride layer. And then I have defined a sparser meshing for the other regions, and then I'm defining a denser meshing in the range of 1.95 to 2 micrometers. So over here in this range, 1.95 to 2 micrometers, I would define denser meshing over here as well, because we have a thin aluminum nitride layer over here. And then I would define sparser meshing everywhere else. The meshing in y direction is running from 0 to 3 micrometers. Region number 1 is running from 0 to 10 micrometers in x direction, and from 2 to 3 micrometers in y direction, and the material is sapphire. So let me uncheck the meshing. Region number 1 is running from 2 to 3 micrometers in y direction, and as you can see from the color chart, the material is sapphire. Now the question is, why did I choose sapphire? Some of the options for growing, some of the substrate options for growing gallium nitride are sapphire, silicon, and silicon carbide. Sapphire is a good choice because there is a lattice mismatch of approximately 16% between the gallium nitride and sapphire layer, which is not a good thing. However, sapphire is cheaper and cost really matters in electronics, so that's why we mostly use sapphire as a substrate for the growth of gallium nitride on top of it. Then I have introduced a thin layer of 20 nanometers running from 1.98 to 2 micrometers of aluminum nitride. And we call this thin layer, let me zoom in on this thin layer. As you can see, it runs from 1.98 to 2 micrometers. This layer, as you can see from the color chart, is aluminum nitride layer. So actually in growth, since there is a lattice mismatch between the gallium nitride layer and the sapphire substrate, we introduce a really thin aluminum nitride nucleation layer to effectively grow gallium nitride on top of sapphire. That is a really short justification for this layer. Let me go back to the code. Region number 3 is gallium nitride running from 0.030 to 1.98. So gallium nitride running from, if you zoom in on this interface, the gallium nitride is running from 0.30 micrometer to 1.98 micrometers. And then I have introduced a really thin aluminum gallium nitride layer, which runs from 0 to 30 nanometers in the y direction. So as you can see over here, this aluminum gallium nitride layer runs from 0 to 30 nanometers, or from 0 to 0.03 micrometers in y direction. And also I have set the aluminum content in the aluminum gallium nitride layer to 0.3. Now here I define the electrodes. First I've defined the source running from 0 to 0.5 in the x direction and 0 to 0.2 in the y direction. So here is my source electrode running from 0 to 0.15 something in the In fact, I need to rerun the code. Okay, in the meantime, while we look at the code, I'm gonna run the simulation as well. Okay, so here is my source contact, as you can see, and because of the sparser meshing, it's not getting up to 0.2 micrometers, but it's close. If I define a more denser meshing, it's gonna go down to like 0.2 micrometers. But since we need the contacts to cover the channel part, so even this width and height of the contacts should be enough. And in order to display the contacts, I right click on the structure, click on display, click on this icon, hit apply, and this is how we display the contacts. So we have the source contact over here. Excuse me. And then the drain contact is running from 9.5 to 10 micrometers in X direction and from 0 to 0.2 in Y direction. So let me close this one since I've run the simulation now. So we have the drain contact running from approximately, I would say 9.7, 9.8 to 10 micrometers, and also from 0 to approximately 0.15 in Y direction. And we are not achieving 0.2 in the Y direction because I've defined a sparser meshing beyond this point. If I define a denser meshing, we can get that as well, but that's not necessary. Then I define a gate electrode from X is equal to 4 to X is equal to 6 micrometers. So once again, we look at this. I will define a gate electrode over here from X is equal to 4 micrometer to X is equal to 6 micrometers on top of the aluminum gallium nitride layer. I'm assigning region the sapphire as substrate, as you can see over here as well. And then I save the structure file with the name of HEMT _ habib.str. Habib is my name, by the way. Then we start another go atlas command, and then we input this structure that we have saved with the name of HEMT _ habib.str. Then we assign a work function of 5 electron volts to the gate, a work function of 3.93 to the source, and a work function of 3.93 to the drain as well. Then I introduce some models. For example, print actually gives us the runtime output. As you can see over here, print gives the runtime output in this window. And then Shockley red hole recombination. I've introduced a mobility model. This actually is an electron. This enables an electron mobility model required for the HEMT simulation. Then I have introduced the polarization model. This model enables the automatic calculation of the interface charges due to spontaneous and piezoelectric polarization. Calc strain actually specifies that the strain is in the region is calculated from the lattice mismatch with the adjacent region. And polar dot scale specifies a constant scale factor multiplied by the calculated spontaneous and piezoelectric polarization charges. It is actually a parameter related to polarization in woodside materials. Then I've used this command of output in order to look at band.temp. Once again, is a useful command to look at so many parameters, for example, conduction, valence energy levels, Fermi energy levels, etc. Then we are looking at polarization charges. For looking at complex band parameters in the runtime window, I introduced this command. We want to look at electron mobility, hole mobility, Shockley-Red-Hall recombination, radiative, OJ recombinations as well, permittivity, and especially I'm interested in current flow lines. This is a useful command if you want to look at where your current is flowing inside the structure. So I've introduced that command as well. Then we are using Newton method for the numerical simulation of the structure, and max strap over here is equal to 20. This actually is a procedure in which if the program is not converging at a specific bias, then it gives a set number of tries in order to converge the program. For example, here we have introduced that we can give it a maximum of 20 tries for the program to converge. For the initial guess of the structure, we introduce this command, solve initial. Then we solve the structure under thermal equilibrium with this name, GaN HEMT1.str, and then we plot GaN HEMT1.str, as you can see over here, GaN HEMT1.str. Then I want to look at the ID versus VGS characteristics of this structure. So for this purpose, I'm going to fix the drain voltage at 5 volts, and I'm running the gate voltage from minus 20 to 1 volt, as you can see over here, with a step of 0.5 volts. And over here I'm creating a log file which is saving all this information. It is saving the ID versus VGS information for this structure. And then I have output the structure under these bias conditions, and I actually plot the structure under these bias conditions as well. So it's HEMT_gate.str. As you can see over here, this is HEMT_gate under the gate bias conditions. Then I want to look at the ID versus VDS, the drain to source current versus drain to source voltage characteristics of the structure as well. So I want to look at these IV characteristics at different gate to source voltages. For example, here let me display the drain voltage. So I hit apply. The program has completed running the simulation. So I want to look at the drain current versus drain voltage characteristics at different gate to source voltages. In the program I'm going to show it to you. I'm using 4 different gate voltages. Minus 6 volt for the red curve, minus 4 volts for the green curve, minus 2 volts for the blue curve, and 0 volts for the cyan curve. So let me go back to the code. Here I have set the gate voltage to minus 6 volts, and then I'm creating a log file for this voltage sweep running from 0 to 30 volts with a step of 0.5 volts. So the drain voltage is running from 0 to 30 volts. And then I save the structure under these biasing conditions, and I Tony plot the structure as well. And then I've fixed the gate voltage to -4 volts, and I'm running the voltage sweep for the drain voltage from 0 to 30 volts with a step of 0.5. Then I have set the gate voltage to -2, and once again we are running the same voltage sweep for the drain from 0 to 30 volts. And then I have set the gate voltage to 0 volts, and I'm running a sweep from 0 to 30 volts for the drain. Then I use Tony plot command. This one over here actually gives me the ID versus VGS characteristic. As you can see over here, this is a drain current versus gate voltage. And this Tony plot command actually, and here I have used overlay. So I actually want to overlay these different ID versus VDS characteristic curves at different gate voltages. And for that purpose, I'm using the command of overlay. And finally, I quit the program. So now that we have simulated the Silvaco TCAD program, I can show you some characteristics of the structure, and also we can look at some parameters, the energy band diagram, etc. So here is the structure under thermal equilibrium, and I'm going to zoom in on the heterojunction region. Here I go to tools, cut line. I draw a cut line across the interface, and then I go to display, and I'm interested in looking at the conduction energy level, valence energy level, and electron quasi-Fermi level. So here is the energy band diagram across the heterojunction. Also, we can go to the structure under a biasing condition of 0 volts for the gate and 30 volts for the drain. So we can look at the energy band diagram under these biasing conditions as well. I zoom in on the heterostructure once again. So I go to tools, cut line. I draw a cut line right across the interface, and then I go to display, EC of T, EV of T, and electron quasi-Fermi level, and do this to make it more presentable. So as we can see, we are applying a positive voltage to the gallium nitride based to the gallium nitride layer, a negative across the gate. So we drag down the gallium nitride side of the energy band diagram, and now we see more band bending under biasing conditions across this interface. Also, we can look at some other parameters. For example, let me disable the energy levels, and let us look, for example, at the polarization charges. As we know, there is spontaneous polarization, piezoelectric polarization right across the interface, introducing polarization charges. So I click on polarization charge concentration, hit apply. So as you can see, we have polarization charges right across the interface. Here is the interface, the reference line over here. We see we have polarization charges right across the interface. We can also look at the current density, for example. So if I click on total current density and hit apply, we see that the current density is also maximum right along the interface. We can also look at these parameters on the structure as well. For example, I click on this plot. Let me delete it. Focus on the structure, and I zoom out on the structure. Now I right click on the structure under biasing conditions at 0 gate voltage and 30 volts drain voltage. So I click on display, click on this contours icon, and then I click on define, go to contours, and here, for example, I want to look at polarization charges. So hit apply, and here we have the reference color chart. So we can see that the polarization are negligible across the structure, but in order to actually see them, we need to zoom in on the interface. We zoom in on the interface, and now we see that the polarization charges are actually confined to the interface between the aluminum gallium nitride and the gallium nitride layer. I zoom out on the structure once again, go to display, and what else can we see? We can also see the total current density. So I go to define, contours, and I uncheck polarization charges, and I click on the total current density, and I hit apply. So as you can see from the reference color chart, the current density is approximately 0 elsewhere in the structure, but it's maximum right across the interface. After zooming in on the heterojunction a couple of times, we can actually see that effect. We can also look at the current flow lines, for this structure. So I go to display once again, click contours, and let me find current flow lines given over here. I hit apply. In fact, this one is much better. So I hit apply, and now you can see that the flow lines are actually confined right across the interface over here. You see like really dense lines of current right across the interface. Now you might see slight divergence of the current flow lines over here at this point, but this is because we are applying a negative voltage to the gate, and this is going to repel the electrons slightly from the interface at this point. And this is more visible for another structure where we have a gate voltage of -6 volts. As we can see from this labeling here, for this structure we are using a biasing condition for the gate of as 6 volts. So if I go to display and then click on contours, go to contours, then click current flow lines, we can see that now the gate, since the gate voltage is -6 volts, we see more repelling of the carriers across the interface right at this point where we have the gate, and that's why we see more diverging of the current flow lines over here when we are using a biasing condition of -6 volts. We can also see the potential across the structure, and for that purpose I go to potential. As you can see, potential is more confined on the drain side, because we are applying voltage on the drain side. Now let us look at the IV characteristics. So here is our ID versus VGS curve, where I've run a sweep from -20 to 1 volts. So this HEMT structure is actually a normally on device. If you don't apply voltage to the gate, we still form the channel, apply voltage to the drain, and current is going to flow between the drain and the source. As we apply negative voltage at the gate, it's going to start repelling the electrons from the channel, as we saw over here. Like at -6 volts, we see that these carriers are now repelled from the channel towards the bulk gallium nitride regions. So and this is at -6 volts. As we keep increasing the negative gate voltage, we are repelling more and more carriers from the channel, and there comes a point where, for example, at -12 volts, now approximately 0 current is flowing across the interface, across the channel, beyond -12 volts. So, and also we have the ID versus VDS characteristic curves over here, where the red curve is at -6 volts for the gate, and similarly for the green curve we have set the gate voltage to -4, for this one to -2, and for this one to 0 volts. We kind of see a long linear region for this HEMT structure, and we actually have control over this linear region and also over the saturation region. And for that purpose, I performed multiple simulations. For example, let me open this file over here. So I performed other simulations as well. Like for example, my reference code is for 30% aluminum content in aluminum gallium nitride, and then I have set the thickness to 30 nanometers. And for this, we obtained. Or let me focus on this curve initially. So for this, we see these characteristic curves. The maximum current is approximately 6 milliamps. I also worked on another structure where I have set the aluminum content to 20% now, using the same aluminum gallium nitride thickness. And now we see for this structure, we see we see that the saturation is actually occurs at smaller drain voltages, but it also results in lower maximum current. Then I also used another condition in which I set the aluminum content to 40% with the same aluminum gallium nitride thickness. And now you can see that the saturation now occurs, as compared to the reference, it occurs way higher for the Sion curve at approximately 25 volts. So we have longer linear region. So the takeaway point is that with increase in the aluminum content in the aluminum gallium nitride layer, the saturation voltage increases. The drain saturation voltage increases. Similarly, let us also look at the effect of the aluminum content on the ID versus VGS characteristic curves as well. So here we see, for example, at 20% aluminum gallium nitride, we see that this point where the channel is approximately totally depleted of carriers is achieved at approximately -6 volts. Similarly, this point is -12 volts for 30% aluminum gallium nitride and approximately at -14 volts for 40% aluminum gallium nitride film. Now, I also performed a comparison of the thickness of the aluminum gallium nitride films. So, for example, I fixed the aluminum content to 30% for all these three cases, and I varied the thickness of the aluminum gallium nitride layer. And then we can see that with increase in thickness, this point, the knee point for the ID versus VGS curve increases. And this is because with increase in thickness, it's going to require more voltage, more negative voltage to repel the electrons away from the channel. Similarly, we have the ID versus VDS characteristic curves as well as a function of the thickness of the aluminum gallium nitride layer, increased from 20 nanometers to 30 to 40 nanometers. And we see that with increase in the thickness of the aluminum gallium nitride layer, the drain voltage, the saturation voltage for the drain increases for these characteristic curves. Then I also wanted to see the effect of, for example, in this structure that I discussed, I am using an undoped gallium nitride. But I also wanted to see the effect of doping on the output characteristic curves. So what I did is that this is my reference ID versus VGS characteristic curve for 30 nanometers aluminum gallium nitride. And then for this one, I set the doping to 1 into 10 to the power of 15 per centimeter cube. And we find that with doping of the bulk region, now this knee point increases for the VGS. So it means that, and this is approximately -22 volts, which means that this device is not going to be off until we apply a voltage of approximately -22 volts to the structure. While for this one, we can turn off the device at approximately -12 volts. Then here are the drain current versus drain voltage characteristic curves for the reference structure. And then for this one is for the structure where I have introduced an electron concentration of 1 into 10 to the power of 15 for the gallium nitride bulk region. For this one over here, the saturation occurs at high voltage of approximately 30 volts for the Sion curve. So that's it for the aluminum gallium nitride based high electron mobility transistor structure for today. And I hope that this session was really useful for you. Please stay tuned to my channel, and I'm really excited and looking forward to posting more videos on Silvaco TCAD and on nanotechnology, especially. I'm going to include some videos on experimental studies as well. Take care. Until next time. Ciao. Dalla Paman.